So yeah, as Marcus mentioned, that this like 1.5 hours we're really gonna be sitting on a laptop and doing some coding. So bring out your laptops for this. But I prepared just 3 slides here to like while you bring out your laptops. So yeah, bring out your laptops. And then yeah, like let's try to keep it like super informal and interactive. So I will like give a lot of time for you to ask questions, because I know there's going to be a lot of questions. But essentially in here now we're going to try to explore all of these ways that you can use to tailor these Nomad oases to your needs. So we're already seeing a lot of like examples of how people have done apps and parsers and schemas, and now we're going to like really take a look at how you actually do this. So like we've already seen an example of these schemas for different labs. So basically this is what you do to define custom data structures and custom functionality. Parsers are essentially these pieces of code that automate data extraction from files. We're going to see an example of these. And also apps, so basically how you could build this kind of a catalysis app that Julia was showing. And yeah, this is like all designed to be interactive. So we have like a Jupyter notebook for you. And in order to access this, all you need is a browser and a Nomad account. So I encourage you now to go to nomad-lab.eu, open Nomad, and then either if you have an account, you sign in. Otherwise, please create an account. It's free. And after that, signing. So I'm just going to wait for everybody to go and do this, and then we'll continue. So let me just quickly show you what it would look like. So if you go to nomad-lab.eu, you press open Nomad. I hope already a lot of people yesterday created accounts, so this is probably you might already have one, but essentially here on the top right, we have this login/register. So you go here, either you register or you log in with your account. I'm just going to give a few minutes for those of you who haven't done this to do this, and we will get started. So while people are doing this, so essentially we have this integrated Jupyter environment within Nomad. We're going to use the central Nomad installation that has this what we call North, like Nomad Remote Tools Hub, which is basically it contains a Jupyter installation there. We're going to work directly, basically, within Nomad to do this exercise. And it's going to be basically Python coding, so it helps if you know a bit of Python, and maybe if you have heard about NumPy, but it's like super basic stuff. So don't worry too much if you don't know even Python. I think if you know any programming language, you can pick up a lot of things from this. Anybody having problems with this? Everybody logged in? Then let's carry on. So now what we're going to do is, maybe I just show you, but we're going to go and navigate to this publish menu here. So in your interface, you will see there's a publish menu, and there should be like an uploads drop down there. And you will go to this add example uploads button. And there you will see a list of things I will show you shortly. And we have prepared basically an upload that contains this Jupyter file that we're going to work on, and we're going to launch it. But just to like really show you what it looks like is something like this. So yeah, publish, uploads, add example uploads. And if everybody is here, basically scroll down a bit. We're interested in this one, tailored research data management with Nomad. And we're just going to press add. And now this is one checkpoint. So has everybody reached this? Any problems with creating this? If not, we're going to continue. So essentially what we just did is we created a Nomad upload, and a Nomad upload contains files, entries, and so on. This particular one it only currently contains files. So here we can see which files does it contain. And what we're interested now is this Jupyter notebook here. If everybody can find this, what we're going to do now is we're going to launch this notebook in Jupyter. And now we hope that the system doesn't crash when all of you do this, but hopefully this will go through. It takes a while to like set everything up. But this is like what we're now going to be forward to is like a live dynamic Jupyter environment that is, it basically all of our data in this upload is mounted here. Let's try again. Let's try after signing out. Yeah, let's see. Okay. Is it now? Okay, let's try stopping it and relaunching. Is my mic still working? Yeah. Okay, good. Let's try again. Okay, maybe looks a bit better. Perfect, okay. Nice, yeah. Okay. Yeah, maybe yeah. Okay, great. So now we're actually in this notebook here. Should I increase the font size maybe a bit? Maybe this is a bit better, okay. Okay, so now the actual like content start, and then everybody is now here. You have your, okay, any problems? Okay, so I would encourage you to do what I did, maybe completely log out, go log in. If it is in this launch state, stop it. So basically you will see if it's in this kind of launch state, you can stop it first, wait a while, and then reopen. Yeah. Try to log in back again. I think this is what if we have a lot of problems, then we would probably switch to like our different installation, but at least the majority of you have been able to do this.
I also see some problems with some.
Yeah, okay. You got in. Okay, perfect. Yeah, great. So essentially ask Marcus if there's any, if there's any particular problems. Otherwise, let's continue, and we're going to have lots of pauses in between to ask questions. Oh, okay, there's quite a lot. Maybe I will just go over the introduction now, and let's wait until everybody's roughly here. But what we're going to do in this notebook is essentially we have this data set in mind now. We're going to use as an example these thermally activated delayed fluorescent molecules. It's just like a kind of not a fake example, but something that will get us started. It's like real scientific data produced. And what we're going to see now, like starting from this data set that contains a lot of kind of fairly not so structured and kind of ad hoc data, how we would now turn this into something that is fair, so findable, accessible, interoperable, and reusable. And we're going to use these different NOMAD concepts to try to do this. So we're going to first like just take a look at the data, like what we are working with. Then we're going to go ahead and design a schema for our data. So you will now actually like see what a schema looks like in Python code and what kind of things you would have to think about if you design your own schema to get a kind of an idea of what this entails. we're going to look at how you can kind of make an ELN out of your schema. So how you would, what kind of, what we call annotations can you add to your, yeah.
Can you ask the people to switch to the staging server?
Okay, so at least those of you who have problems, go to the staging server. So essentially I'm going to show you here. So if you go back to nomad-lab.eu and you scroll all the way down here, there is this staging server, which hopefully is now more stable for you. It's essentially the same thing, contains the same notebook and so on, but just switch here. You can use the same login, same credentials work here, everything looks the same, the data is the same. So if you have a lot of problems, go here and try it here. Follow the exact same steps, I think here. So there's going to be the same example upload in here and so on. So you just go here. Once again, ask more if you have any problems with this. But yet, I'm going to slowly go on to the contents, and we'll have maybe like a brief point somewhere to ask you where you got. Okay, so now let's gonna start with this first section. So let's take an overview of the data that we are working with. So as I said, we're going to start out with this TADF data set. So these are, I don't know much about the physics or the chemistry, but these are some type of molecules that are key in, for example, in manufacturing of OLEDs and some other applications. And yeah, this was some data that is now has been published by these people, and the original data was actually extracted using these natural language processing tools from publications as well. So it's kind of crawled data, and these are kind of raw files that we're going to work with are basically JSON files that contain a few key things about this molecule. So there's the SMILES. This is kind of an identifier for this molecule used in chemistry. There's the DOI from which publication this data was extracted from, some compound names, and then some interesting measurement properties, measurement results that were basically extracted and done from the papers that are now linked to this molecule. So this is roughly what our raw data looks like, and we're going to start here. What we're going to completely skip is these 40 hidden cells, which actually would tell you the full story of how you go from this CSV file somewhere hidden deep within this, in Zenodo, and create and clean and do all kinds of things to get to this JSON file. But that's not the point of this tutorial. But just keep in mind that this is a lot of work typically that you will have to do. Like the data cleaning is it's a big topic. So you cannot typically assume that you can just start working right away on this scientific data. There's always something that you need to do, some unit issues, some inconsistency that you will need to handle. Now with this raw data in mind, let's go on and design a schema for this. So schemas in NOMAD are basically these kind of templates which define like what sort of quantities, what sort of structures, how do you want to structure data, how you want to create descriptions for different pieces of information in your data. So it's kind of a now when we go from just a fairly uncommented JSON file into something a bit more fair that people could actually understand better, this is where schemas come in. And in this case, because we're talking about molecules, so it's kind of natural that we want to create a schema that describes a molecule. We could go some other way around. We could, for example, create a schema that describes an experiment that is connected to a sample and so on. But in this example, we're going to go with a fairly easy approach. So we're going to basically describe what we think these molecules are and what kind of properties they have. So you can see here, we can run this cell now here, and what it does, we're basically defining a Python class here called TADF molecule, and what you can see here, it inherits from schema. So this is now where the NOMAD functionality comes in. And essentially, you can think of these schemas, they're very, if you're familiar with Pydantic, raise your hand if you've used Pydantic, if you know what Pydantic is. If not, then I'm not going to go there. But essentially, these classes are contain these what we call quantities. So this is essentially a container for quantities and possibly also for subsections. And quantities in NOMAD are some sort of actual pieces of data, so numbers, strings, arrays, actual concrete pieces of data that you want to store. And classes are what we call sections, or these are basically just containers for these things. So in this particular case, the schema contains 4 quantities, one for photoluminescence quantum yield, peak emission wavelength, delayed lifetime, singlet triplet energy splitting. So essentially what you can see, we're just taking a look at some of the interesting things from the JSON that we really want to now put into our schema, what we're interested in. We picked these, and now we kind of fleshed them out here. So it's no longer just like a name, but it also has like a data type, description, sometimes unit as well. So this is like really, we're starting to make it more fair in this sense that people could actually now understand what we're storing here and reproduce some of this if they know a bit more. But yeah. Yes. So basically here you could do any, for example, it's a string because of this is typically how you would input it. And you can use mathematical expressions, for example, here to say meters per second, whatever you want to do here. And it's basically based on the unit you give, the physical dimension is like automatically inferred. From the unit, yes.
But if I would write some string you didn't know about,
you'd get an error. Yeah. Yeah. So let's see. I actually don't. Let's see. I don't know. Let's see if we get an error or not. Yeah. Okay. There is something saying that. I don't know what kind of an error are we getting. Yeah. Okay. It's not defined. So this would hopefully help you. Okay. Now I don't remember what we have. Okay. Nanometer. Okay. Okay, and then just to like as a fun fact, you can like use a lot of things in here. Like all of these SI units are or SI prefixes are available, and all kinds of things you can do in here. Okay, let's go back to maybe nanometers are a bit more sensible. Okay, yeah, I basically already covered this. What I don't go too much into details is basically this is to keep it simple, it's like one kind of a container, and the 4 quantities. What you can, of course, now do is think about in a more realistic scenario, you have subsections and quantities within subsections and repeated subsection, things like this. So all of this is possible. I'm just like showing the simplest thing that you could start out with. And now to have like an idea of what you can actually do with these schemas and what kind of tools we've built on top is, so okay, now we can actually instantiate like an instance of this schema. So like typically in Python, you basically are calling the constructor for this class, and you can in here, don't do this. Maybe I restart. Okay, it doesn't like me anymore. Neither on staging. let's see. Okay. Can I restart?
Which is also super annoying because you have to re-execute already.
Yeah, but no, we're on second cell, so it's not. Okay. Okay. So let's go back.
On the top right next to Python, after kernel, it says like write to that symbol, write to that says
Okay. So let's see. Yeah, let's see what it thinks. Is it like running here or not? I think it's still running. Okay, let's see. But you said also on the staging it's as unstable. Any experiences on there? Maybe I switch here. Let's see if it's any better here. Yeah, so unfortunately seems to be a bit random.
I think it's more the servers themselves. It doesn't really matter what deployment you're using.
Yeah, okay.
I think it's just too much stuff going on.
Could be.
But I'm wondering why, because we had larger audiences.
Yeah. I don't know if there's some other traffic going on. Let's try our best. I hope that many of you are still able to follow along, because this was kind of the idea. Let's see. Does this run? Yeah, okay.
One thing that we can try, at least that he can continue and show stuff, is that all of you are just stopping the servers now. If you can reach the point. And then we can at least see if the situation improves.
Yeah, this one, it's a bit unfortunate. Of course, then these are...
Monitor the resources, it doesn't look too bad, but I just have no idea why.
Yeah, okay. But essentially, this is going to be there for you to play around with later on, but of course, this would be the best place for now for you to follow along. Okay, I guess we have to continue just in... because time's running. So essentially, you can see here that now we can instantiate this schema and we can give values for these quantities that we defined. This is one way to kind of start populating these fields. You can also set them later on. So this is basically the instance of the schema, and you can add this delayed lifetime now here later if we wish. Also, this unit information is now carried along when you set or get quantities. So let's have an example of this. What I mean by this. So here we can set, for example, this energy value by giving it some numerical value times a unit. So we have this what's called like a unit registry where you can fetch these units from, and basically with a multiplication you can kind of attach them to some numerical value, also to NumPy arrays, things like this. And this basically now supports everything that also these schemas support. And now when you set it in here, you can, and we are now printing it out after setting it, you can see that basically the joules were automatically transformed to electron volts because we defined that we want to have this in electron volts here. So this is kind of a way to, because this is something that will happen to you at some point. You mess up the unit. So with this, you have at least some kind of idea of how these are preserved, and hopefully don't do as many mistakes if you carry these units along. There was a question?
exactly that. So what you define the schema is not really the only allowed unit, but it's the default unit that we basically
Stored. yeah, it's exactly, it defines the unit that things will be stored in, because we need one decision there, yeah. And then, of course, you can transform it, like the GUI does a lot of this, so you may display it in different units. Also, during your work, you might want to use some other units and so on. Okay, so now we basically see that our schema gets populated with these values. We get some work done with this. And essentially, if you're, for example, writing a parser, what you would do, we will actually see this later, is that basically you're going to just in your Python code, you're going to maybe you read some file and then you populate this schema with these values, and hopefully don't mess the units up. This is like often happens. But like we try to like support these units like all the way through. So if you're, for example, now reading something out of this, like we did here, this is actually not just a number, it's a number attached with a unit. And if you now assign this to some other parts of the schema, the units get carried along and the transformation are done automatically for you. So this is kind of like a nice feature. Okay. Now that we, yep. Well, this is actually like coming from an external library. So we are using this bind library that exactly kind of does this. So you basically defines what does it mean if you multiply a number with a unit, and it. Yeah, this gives you like a Python object that has this. Yeah, exactly. And the nice thing about it is it also works with NumPy arrays, so you can attach a unit to a whole like 3-dimensional array, for example. Yeah. Okay, let's move on. What we're gonna now look at is what we call base sections. So we have now like an initial draft of our schema and some quantities in there. But what you can do, so you saw that we were only inheriting from schema. Now let's inherit from a couple of more things. And what this inheritance means is that somebody has written another type of a section, which now we can kind of use in our own schema. What this inheritance essentially means that this is another kind of a section that defines some quantities in there. For example, this pure substance section, I think it has fields for some chemistry related things like Inchi and Smiles and so on. So what we're doing here is that we're inheriting those quantities. They don't show up here, but we're kind of silently getting them along into our schema as well. So we're going to see now that if what the difference is here, that we just added these. It's like a multiple inheritance kind of situation where we're getting stuff from here and getting stuff from here as well. And we're going to see like an example of this. So now, suddenly with this small change, we also have something like molecule.smile, which is where we can set values. And we also got a DOI number from this publication reference. So now we've kind of extended our schema to have more quantities in there from this. And this is kind of a useful concept where you can basically, this is all about like reusing the ideas from other people, from other labs. What we think, for example, in FAIRmat are these useful base sections. We have like a collection of them. And this is all about trying to make things more consistent. So I really encourage you to think about what kind of sections you could share with others and maybe reuse from other people. So this is always kind of useful exercise before you go and try to think of your own structure. So this is like I think an important point here. So to try and look at these base sections and what you can do with them. So now, until now, we've only looked at basically data structures, or what kind of quantities you can have, what sort of sections you can have. But another very interesting concept is this kind of functionality that you can also introduce to your schema. So it's not only about data structure, but also about functions that you can invoke. And basically your schema and any section within your schema can have this normalize function. And what this function does is essentially that any time that somebody modifies one of these values, this function is run. And here you can do all kinds of things with these values. So typical actions that you might take is that you perform some validation, you maybe create some derived values, you might do even like an API call, like we saw, I think, yesterday we saw an example of this, like basically you only filled the kind of name of this sample, and then there was an API call that fetched from PubChem all of this other information in there. So this is like the point at kind of the attack point where you would add all of this functionality in. It's this normalized function. And now we as I said, we're also inheriting from other sections here. So you can also call the normalized functions of those upper level sections. So this is where you to kind of inherit also functionality from them. And then on top of that, you can define your own functionality in here as well. So inheritance is not only about data structures, but also functionality. Yeah, let's go here. So here, this piece of text is now going to try to explain to you what these arguments are. So the archive it's basically the root level section. It's the top level section that all entries in NOMAD have. So this is like where you can where all of the data that is currently in this entry is stored, and you can access any parts of it. So that is what an archive is. And then we have also a logger, which is basically a place where you can put log messages in. Whether it's useful for you or not, it depends, but at least for us it is very useful because here if you log, for example, if you catch an exception or you think that something unwanted is happening, you can essentially call these log methods something like logger.warn, logger.error, and these actually in our system they get collected and we can investigate these logs later on. So at least for us in the central NOMAD, these are very useful for debugging and investigating what is happening. And then it depends on your use case. For example, in an Oasis, you could log also these kind of things and then investigate, for example, if you're having some issues in your schemas or some performance problems or anything. And these logs, basically, they get stored as part of your archive, so you can directly investigate them. We will probably, maybe I'll show you an example of that as well. So these are the two arguments that we're getting. Archive is basically so that you can read some data and also write some data to this overall archive that we are working with. And what this archive, so as I mentioned, is like this top-level container, and it contains a few different, automatically set subsections. There's one called metadata that basically contains things like what is the processing timestamp, what is this entry ID, and so things, typically you don't need to touch this at all. It's something that we log automatically. And this is just to keep it separate from what we now actually think is the data. And this is another subsection there where actually we will be, so this archive.data is essentially where all of these things will be stored. So the quantum yield and wavelengths and these things will go there. So this is what we consider the actual data in there. And we also have this results section, which is the third main kind of a place where you might want to do things. And we will actually have a complete separate section about it. I will explain a bit more there. So yeah, as I said, now like basically this archive.data is now holding this instance of our TADF molecule. So this is where we can interact with it. And yeah, the logger I already explained. So now let's try to do something actually interesting in the normalize function. So I hope I ran this already. So what we could, for example, now do is that let's calculate the molecular weight based on the smiles that we basically now have. And we're going to install RDKit for this. So this is like a Python package for doing these kind of things, getting molecular data from smile strings and doing things with this. And just for clarity, basically I created another function here that it gets called, just in order not to always define this redefine it. But essentially you can think of this my normalization now, this is now the normalized function that we're calling. And what we're going to do here is that essentially self now refers to our schema. So self.smile, we saw that smile actually it's now inherited from this pure substance section. So smile is one of our quantities that we can work with. If self.smile exists, we're going to read it and create an RDKit molecule out of it. So this is like, you don't need to know the details. It's basically like some Python object that now represents a molecule. With RDKit, we can do things like add some missing hydrogens. I think it's this function. And we can actually also get the molecular mass formula and mass out of RDKit as well. So this is a fairly simple normalized function that just, if smile was written, let's extract some derivable information out of it. Yeah. Archive.data.smile, it's the same thing. Yes, exactly, because sometimes maybe you need the whole, like the archive might contain more, and typically also when you write something to it, you might want to jump out of this data section. We're going to see an example of this, like the results section is actually quite important, so often you want to write stuff there. Not part of self, yeah, exactly. That's why we need the top level, yeah. Mm-hmm. Okay. And because we are in this Jupyter environment, we can kind of now fake call all of this. So normally, like all of this stuff in cell 8 would be like handled automatically for you, like this, calling this normalized function and setting these things up. But because we kind of want to show you what really goes under the hood, this is how you would call it. So we essentially, this is the top level container, this archive. It has a subsection called data. We are putting an instance of our schema in there, and it has smile and DOI number. So this is now the archive. And if you remember, archive.data has a normalized function that we can call, and it takes in this and this.
So this is just a hack to avoid normalizing.
Yeah, it's in here it looks a bit too complex because we just want to demonstrate this on this notebook environment. All of this would be kind of taken care for you if you're just processing that. Basically, exactly. You just assign these, and these will get automatically called. Exactly. Okay, so I think we got something out of this. So let's see if this actually did what we wanted. So we are printing out this archive.data as a dictionary, m2dec, and we're like creating like a JSON representation out of it. And we can see that, okay, this smile was put in there, the DOI number was put in there, but also the molecular formula that we now calculated here, and the molecular mass was calculated here, and these are put in there. And also, importantly, you can see that there's something else that we may not expect, unexpected things happening here. There's also publication date that is being filled, journal, publication title, and these essentially come from here. So we called the normalized function of our base classes, and this base class, publication reference, is doing all of this. Okay, hopefully you roughly can follow along this. Okay. But this is an important point, like this inheritance also, you can inherit functionality, and whether you want to do it, you could, for example, want to skip this completely. I don't know, it depends now. You have quite a lot of freedom in these functions to decide what you want to do. Okay, let's take a look at this, like jumping out into the archive and seeing what we can do on the top level container. Okay, so this archive.data this is our kind of world that we're now living. It's our custom, like completely customizable data structure that maybe your lab wants to have, and so on, and all good and fine. But now making this interoperable with other types of schemas is a bit trickier, and this is where the results section is supposed to help. And we have basically this section where where the structure is now fixed. It contains things like there's something called results.material.chemical formula, something. So it contains these kind of formulas, for example, that are kind of universal. It contains things like what is your elemental composition. You can store full 3D structures in there. It also has a lot of places where you can store physical properties like band gaps and so on. And this structure is fixed. And why this is fixed is to make it interoperable between different schemas. And this is where you often want to like now put, that's why it's called results. Maybe it's a bad name or not, but this is where you would put the final things that you want to now like kind of advertise that out of this work that I did, these are the things that I want to like really like expose to the world and expose also to the search interface. So a lot of the things that you saw in the search interface is working based on this results section, because we cannot just somehow figure out that in your custom data schema, where did you store this formula and in which format and da. So this is where the results thing is like a fixed and kind of in a sense very, very fixed structure that helps with this searches and interoperability. So let's now see an example of what we could do now in this case with the results section. So yeah, it's stored in archive.results, and this I already went through. And now let's imagine that, yeah, people wanted to do a query, something like in the GUI, basically, when you clicked on those periodic table, this is what is going to like look for results.material.elements and then like a list of elements. So in order for our entry to be foundable, we need to populate this. So let's take an example. So we modify the normalized function a bit. So this we already had. If self-smart, and this is what we're now adding on top of it. So we are actually also with RDKit, we can fully make a kind of a reconstruction of the full 3D structure of this molecule. This is what we're doing here. And if there's an error, we kind of halt the whole process because we think that this is like a really serious thing. We want to fully halt the function here. But if everything goes fine, we go on. And we're saying here that, okay, if this archive.results.material does not exist, let's create it. And we're putting all kinds of formulas in here. We have this kind of a helper function to do it. So this is like a class where I can put in a formula and call a populate function on it to populate things into this particular section. But you could do all of this by hand. Basically, what you need to do is that you now in here put something like chemical formula hill equals that, and chemical formula, what are the other options, like UPAC equals that. You could do all of this manual, but this is just like a convenience function that does a lot of the work for you. And then what we're going to do as well is that we actually want to store the full 3D structure of this molecule now in the results as well. And this is how we do it. We are essentially taking this RDKit molecule, getting the atomic positions, atomic numbers, making them into an ASC atoms. This is just to mangle the data around a bit to get it in a more nicer way into NOMAD. And we're going to create what is called a system out of it. And system is once again one of these, I guess you could think of it as a kind of a base class, which represents now some kind of a sample, some kind of a structure in the data. And you can see that it has fields like, okay, you can give it atoms, which is like the full 3D representation. So sometimes you can populate it, but in experiments, for example, you wouldn't have this at all. But there's other fields that you can populate, like a description, what was the structural type, dimensionality, and so on. So now we're basically creating this one, and we are adding it to what is here called archive.results.material.topology. And this is kind of the topology is, for our case, it's like too complicated of a thing, because we only have one molecule that we want to store. But the topology essentially is there because it allows you to have all kinds of very complicated logical connections between different types of systems. So a system might have a subsystem that has a subsystem that has a list of subsystems. It's kind of like a tree. I think we saw some examples yesterday. Basically, now if we populate this topology, what we're going to get in this graphical user interface is this like a tree which we can browse to see like different parts of your material. And it could be a solar cell device that has layers. It could be MD simulation, which has groups of molecules, which have some proteins in them. This is kind of very flexible way of you to represent different structures and their connections. So this is what we do here. Essentially, we're populating these two for our tools, for our visualization tools to pick up on and show something interesting. So let's run this cell, and let's also now what we're gonna go and do is now we're gonna do the same thing that we did in cell, I think was it here. We're just going to call this normalized function that was now modified slightly here. And let's take a look at what happens here. So this is just like a warning. We divided something by 0 and everything exploded, but it's fine for us. We have essentially now, we're printing out archive.results as a kind of a JSON structure. And we can see here that essentially this formula call here populated a lot of these formulas for us. So there's descriptive formula, reduced, hill, UPAC, anonymous. We also got a full like elemental composition out of this. So there's carbon, hydrogen, nitrogen, oxygen here. And also this topology is now here. So for our case, it's very simple. There's only one element in here, but this is essentially a tree structure where you could put a lot of things in here, and you can see that here we actually have full 3D structure stored here as well. Okay, so far so good. Let's take maybe a small break here now to get like some time for questions before we move on. So any questions so far? Any luck in getting anything to work with your laptops, or maybe you didn't try anymore? Maybe it's better if you just follow along. Yeah. Yeah. It's I think.
If you want to, just go ahead and try again.
If there's no more specific, yeah, I've got a question.
I tried to use the unit degree Celsius, so I changed it in the schema and also debugging. I tried to design, and then there was an error appearing, which is something like offset unit problem. Has this ever appeared before?
Offset unit problem. I've never had this, but I think this is fairly typical thing that I don't know what could be wrong there. Like it depends on what value you were trying to assign to it. Were you trying to assign just a plain number to it? So this should work, yeah, definitely. Maybe there was an issue in your unit definition, and maybe, I don't know if you remember which exact, I think it's degree _ Celsius is like what it's called. That might be a problem, yeah. Yeah, okay. Yeah, I think in these, in the schema, you're not, it might, yeah, because these are basically probably some Python variables, so they might have, you cannot use the special symbol. It might be something like this. Of course, for example, in the GUI, we then use a lot of these abbreviated and nicely formatted like symbols for these. But in the schema, you might have problems if you use these kind of degree symbols. Yeah. Okay. Let's move on. We still have like half an hour here. So what we're going to do next is that now let's really transform this into an ELN. So far, we have this data structure down, we have some normalized functions, but if you didn't do anything further, this would not be editable in the graphical user interface. So now to create this, make this into a kind of editable ELN, we need to add a few annotations. And annotations are basically just these pieces of or additional properties that we can give to these quantities to tell our graphical user interface, okay, I want to show a component, a number edit quantity component for this field when somebody's viewing this data. And with this, you can control a lot of things, like some things you may not want to show at all to be editable at all, so then you don't give the annotations. You might decide that, okay, something needs to be a slider, something needs to be a drop down. So this is like where you can control now how the user interface is going to look for these things. And here we're doing a fairly simple thing. We're just saying that all of these should be number edit fields where people can type in a number, and that's it. But I can encourage you to take a look at these links where we basically tell you a lot about what sort of annotations we have available. This is actually where you can test them out. Like there's different kinds of things here. There's the sliders and date times and also this rich text field. And this is like a playground where you can check them out a bit. And then there was this other link that forwards you to the documentation. And here you can see really what sort of things you can actually set in these annotations. And this will probably be very helpful for this. Okay, and now just to give you an idea of what this would really look like now in the GUI. Did I run this one? We can actually, just to kind of demonstrate for demonstration purposes, we can now we already saw yesterday an example of you can define these schemas as YAML files or as Python. So far we've done it in Python, but we can actually serialize this as the corresponding YAML version as well. And this is what we're going to do here. We're going to serialize this whole thing as a YAML file, and we're going to actually put it directly in this upload. So in basically in these notebooks, you can also create files into the upload. So when I ran this, you can see there's a new file created here, and this is actually the YAML schema now. This is created from this Python version that we had. And the purpose for this is basically that now we can actually even see it in the graphical user interface like we did yesterday. So if we now go and want to explore what this schema looks like, we can go back to this upload that we had. Basically this notebook created a new file here, but it's not yet picked up by our system. So we need to reprocess this upload for this schema to be picked up. And now it's kind of available for us also to create entries from. And essentially, let's do that now. So now we can create a new entry from a schema. And we called it something like TADF molecules, I think. And maybe it's this one. Yeah. This is our schema that we want to use. Let's call it a test, and let's create an instance of this. So now you can see that what this schema would look like as an ELN. So what you can see here, there's lots of these things that we defined. So there was peak emission wavelength, where we said we want to number it, quantity, delayed lifetime, this energy. But there's also other things coming from the base classes, from the base sections. So there's DOA number, substance name, Inchi key, smiles. A lot of these things came from the base classes for us, kind of for free. And this is like how this schema would now look like as an EL. Yeah.
So you actually create the schema using Python code,
Yeah.
and you have to do this reprocessing so that you could actually execute that code. You could have executed, no, you did execute Python directly into the schema.
Yeah, okay.
File, but that wasn't immediately recognized as a schema until you did reprocessing.
Yes. So
Could you also have, if you knew how to do it, have simply written the YAML, uploaded that?
yes, yeah.
So the two are absolutely equivalent. You can do everything in one and the other.
Okay, so
Including normalization.
that's the part where it breaks. So the YAML schemas, like data structure-wise, they're equivalent to the Python ones, but yeah, you can't define a normalized function in a YAML file because this is quite a dangerous kind of thing that if you could do this like for anything. And then like the whole point of this exercise that we're doing now is I just want to show you in this notebook what it feels like to write these things in Python. And basically at the end we're gonna see how you would make these into what we call plugins. And if you have these plugins installed on your NOMAD Oasis, you don't then need to do you don't do anything with the YAMLs anymore.
But if I do this manually, so you actually need this YAML file to be able to use your code as a schema.
Yes, basically you need this YAML file somewhere for us to create all of this. Yeah, to create the UI. Basically, this is creative.
Does this YAML file contain a reference to the class which is normalized now? Because otherwise, how would this UI know that there's a bit of extra stuff which is not in the YAML file, which is part of this class?
Okay, so this YAML file doesn't know anything now about our Python code. Okay, so it only knows that there's a YAML file which defines like a schema, and it has this is where it links. So basically, there is a link between these two. Yeah.
So here, if you fill this form out, the normalized won't run.
Exactly. Yeah. Exactly. Let's go back. And this was also part of this exercise, kind of getting this like idea. Like the YAML files are really kind of nice for getting started at least, and you can do a lot with them. But yeah, there's this, like that the normalized function is not available there. And this might be a point where you might want to think like, okay, maybe I want to do this in Python. Depends on the use case.
So there's another way to register.
Yes. Okay. So we still, I think we are pretty much on time. Let's go on to parsers. Oh. Yeah, so did you reprocess the upload where you put the YAML file in? Okay, Marcus will come and help you. Thank you, Marcus. So in the meantime, let's slowly move on to parsers. So now, like what we've done, okay, we designed the schema, we designed a normalized function and an ELN, and this is all fine for a lot of, for example, lab work, where you'll do a lot of manual filling of these things. But often, yeah, you want to automate a lot of things. And this is where parsers will come in. So often it's not so much about people filling forms, but it's more about different devices produce files that you want to automatically extract information from. It might be some simulation software that produces these files, or maybe some colleague has produced a CSV file and you want to kind of parse this. So there's many different use cases, and essentially this translation of these files into NOMAD entries is where parsers come in. So parser is simply like a small piece of software that gets triggered on a certain file and transforms it into a NOMAD entry. That's the main idea. And let's take a look at what would it feel like to write a parser. And this is like a very simple example of this. So we have these base classes, like we had like a classes for schemas. We have one class for parsing, or actually multiple ones found from here. So we're going to use this base class called matching parser. And what a matching parser does is that essentially in the constructor you can say which files will trigger this parser. So you can say something like, maybe something in the file name triggers this. Often this might be enough, but maybe not. So then you can have additional conditions, something like maybe the MIME type needs to be of a certain thing, or even maybe the contents of this file need to have something in them. So this depends on like how far you need to go in order to distinguish this file. Quite often, at least, for example, with simulation software, we need to read, like there's some header in the text file that we need to match, okay, that this was a VASP or a exciting calculation, whatever, to figure out that, like, okay, this is now where the parser needs to come in. So one part of these parsers is like what files do need to be matched, and the other part is like the actual parsing. So this parse function is essentially it's getting now some main file as a file path, and this was already like the matching what has happened, and this is supposed to be now a file that you can parse. And this we already like saw what these archive and logger are. So basically these are the exact same things as in the normalized function. So this is now like a new archive created which we wanna populate, and there's also the logger. And now the parser can do a lot of things in here, and basically what we can do is we start out with kind of a plain archive where we can even decide, okay, now in the archive.data we want to use a certain schema and this is what we're going to do here. So let's expand this a bit. So this we already covered. So let's expand this a bit with actually doing something here with this parser. So we say now, if you remember from section 1, we are working with these JSON files. So this is our data that we're working with. And now let's create a parser that from these JSON files transforms them into archives that use our schema in them. So this is the process that we're trying to do. So what we do here is we get the main file, we open it, we know that it's a JSON, let's load it into a Python dictionary here. Then we know, okay, these files should be made into this schema that we defined. So this is the TADF molecule schema that we already have and have defined, and we can now fill in some of these things. So we remember there's a DOI number that we now get from this dictionary. There was the abbreviated name, UPAC name. There's also the smiles, and so this parser is essentially now reading this raw file, filling this schema. It's also extracting these measured properties. So if let's go back here, it's basically this file that we're working on, and it has these different fields that we're now reading in and populating the schema with. So we're getting these 4 measured properties and putting them into our schema instance. And we are also including the unit information here, which is once again super important. So basically in this JSON file, it is saying that this wavelength was in nanometers. And if there's a mismatch between what the raw file contained as units and what your schema defines, and you don't carry this thing over, you're going to have nasty problems. So the units, I cannot stress that enough, that these units are important. So we carry on this unit information by doing exactly this, actual numerical value times this actual unit definition, and then we set it inside the schema instance, and then automatically the conversion is done. And importantly here, you can see now we are actually, though previously this archive was completely empty, now we said archive.data is actually the schema instance. Now we populated this whole thing. And let's see what happens. So we're going to call this kind of, once again, within this notebook, we're going to do a few extra steps here because simply because we are in this notebook environment. But typically, like if you would register this parser into a NOMAD Oasis, all of these calls will be done automatically. So you don't need to worry about the matching too much if you've just like said what are these conditions. You don't need to do any of this like with code at all. So our processing will automatically do this matching of the files and calling of the correct parsers and things like that. But in this notebook environment, we're just calling them explicitly. So we saw that, okay, what this parser did is now that we're looking at this data section. So we populated exactly what we expect to be populated. And once again, in the notebook environment, we will need to explicitly call the normalize function. In a typical production environment, this will be called automatically. But now you can see that this normalize will then work. What we already defined for the schema in this normalize function, this can now work on top of the parse data as well. So what it has done is exactly the same things that we saw before. It has added this results material, all these formulas, and so on. But also now here this data is in. Okay. And one an interesting thing to notice here is that it's not always clear how these responsibilities between these different parsers and normalizers should be split, because they're kind of doing the same thing. They're just sometimes they're deriving some values, sometimes they're reading something. So it's not always super clear, and I think it's kind of sometimes fairly impossible to make a really clear distinction. But at least in our case, it's kind of nice to think that, okay, the parser is basically doing what the people in the lab would do if he were to fill the ELN. And then the normalize is doing everything that we want to automate, both for the parsed files and for the human inputted data. Yeah.
But it's one important difference. Parsers will never run once when you import the file to entry. Whereas the normalize,
Yeah.
every time you put the
Yeah, that's also a distinction. Yes, yeah. But then it depends. Sometimes you wanna, for example, skip. You don't want to do any normalization at all, and then you let the parser do everything. But this is typically where there's no human involvement in the ELNs then at all. This is, for example, in the case of simulations, this is what typically happens. There's no human involvement. You're not tweaking the energy values of your DFT calculation. Yeah. Okay. Or hopefully not doing that. Okay. And then, yeah, what we can now actually do here is just to give you an example of what these things would look like in the GUI. What we're doing in this cell is, once again, we're kind of calling this parser manually on these files that we have. So we have this folder that contains a lot of these JSON files. And we are now triggering kind of manually this parser on them and creating the archives and setting up these schema IDs correctly for you. And all of this is just in order for us to take a look at what these entries would look like on the GUI. So there's not much important things that you might want to understand in this. The point is that now we are going to create entries in our upload that we can view here. And now you can actually see that one of our structures basically made a log here. If you remember, we have this condition here that if something here goes wrong, we are logging this message. So one of our structures, for some reason, this molecule creation, this 3D structure creation failed, but we get a log message out of it. But otherwise it looked fine. So we basically now should have something in this folder. Yeah, so these are now the archives that were created by the parser, and the normalizer was run on top, and so on. Now let's have a look at what these look like. And once again, whatever we do within the notebook, if we created some new files, our system is not automatically aware of them. So then what we need to once again do is that we reprocess this in order for the system to pick these up. So let's now see if we get more entries in here. So now, besides this YAML schema that we created, it is also an entry. We're also now getting these molecules in here. And so there should be, there's 22 entries. Let's take a look at one of them. So here you can see now this first card kind of shows what our schema contains and all of this information that we kind of would expect. But also, because we filled now the results section, this card is getting shown up. And this is kind of we now see the full 3D reconstruction because we saved it in this topology. If it were a more complicated tree, this would be a kind of a foldable tree that you could explore and so on. And it contains all of this composition information and so on. So this is just because we populated the results section, we get all of this kind of for free. This visualization gets done. Also, the search now can be done on these formulas and so on. Okay, great. We could explore more of these, but they do look kind of similar. All of these have this molecules and the chemical data in here. Okay. Now yep. If we decided that our entry, this topology, we want to show 100 molecules in there, that's our decision. Whether that makes sense, I don't know. But there's always this, somebody needs to make a decision of what an entry is. Is my entry a collection of molecules? Is it a single molecule? Is it a library of molecules? So this is something that when you're designing your schema, you really have to think about. But there are, we provide these different tools and we try to accommodate quite a lot of things. So for example, in the search interface, you can do quite a lot of things with individual entries and kind of aggregating this data. So what we're, for example, planning in the future is that we're going to have this kind of a gallery where if your individual entries are individual molecules, we might have some sort of a widget that would show you a gallery of the molecule 3D representations of them. So but there's like different levels where you might want to tackle this problem. Like either you make the entries more fine-grained, or then you collect them already there. But this is kind of to some degree, a decision on your end. Yeah. Okay. And now we have 10 minutes roughly left. So what I now want to do is to go back to this question of what does an app look like. So there was this question of like how much work would it be to define this, for example, this catalysis app, and what we've been able to do in the past few months. We also made it so that these apps can be defined in Python as well. So previously they were YAML based, but now they can also be defined in Python. And I'm just going to show you like an example of what an app might look like in Python. So it's something like this. I'm not going to go too much into this details. I'm just going to show you the end result in a few minutes. But you can see here some important things. So basically, an app, we have a model for this. What we think an app is. It defines certain very important things like what is the label, what is the path in this, like in the URL for this app. There's a description, there's a type of category for this app. There's also something which decides which sort of search filters you want to enable in this app. Often you don't want to enable all of these search filters because you would have quite a hard time with, for example, in the search bar, if you have all like thousands and thousands of different filters that you could fill in. If you type in something like a energy in there, and if you have 1,000 different things to fill in, it might not be what you want. So you may want to kind of restrict what sort of filters you want to show for this app. So this just controls the searchable things, what you can type in the search bar, what you can interact with the app in. We're also defining a locked set of filters. So this means that this app, even before you do any queries on top, it has done like a pre-filtering for you. So typically this is something like, okay, I want this app to only work on entries that come from this schema. Then this is exactly what we're doing here. We're saying that all of these entries that this app shows must have in their section definitions our schema name. So this is like an identifier for our schema that you would use in Python. And we're saying that, okay, this app shows only these things. But you could, in this pre-filter, you could do all kinds of things. You could not define anything in here, and then it just fetches a list of all the entries. It's like a mixture of all kinds of things. Also doing something like how do we want to paginate things in the results table. We're deciding which columns we want to show in this results table. So in this case, we're gonna pick up some things from our schema, and maybe we only want to show 2 decimal places in there, and what are the units we want to use in the display. So this is like the distinction, like everything what you said in the schema tells how we store, in which units we store things, and this now controls if you want to change it. I want to display it instead in some other units. So this might happen, and this is how you do it. We also say something about what are these filter menus. So maybe it helps if we go in. So this was the columns that we've controlled, and these are now the filter menus that we're now controlling here. So we say that in this app we want to show like this material and something about elements. This section is like kind of fairly rigid, so you can't do very much with these filter menus yet, but we're working on improving this, so you could do a lot more. And like one very interesting part is this, what we call dashboard. So you can control like these default widgets. For example, we have a calculations app, which somebody has decided that we want to show these widgets in here. And this is what we're controlling here. So in this case, we're going to want to show the periodic table, some scatter plots, so on. Let me just like show what it looks like. So now you get a feeling of how much code and how much effort you need to put in to define this, and then the actual end result we cannot somehow mimic in this notebook, so we prepared it in one of our demo oases here. So we have this app like installed into this particular oasis, and you can see here that it's now we define that we want it under experiment category. This is our name for the app, and if we go here, we're basically now seeing these widgets that we defined here, and these menus as well. And these are now, we prepared this for you, so that, let's bring this zoom level to the regular. So this is how it is designed to look like. So these are basically now these entries that we work with. So each one of these is a molecule, and we defined a scatter plot of this quantum yield versus wavelength here, and some histograms. And now we can, for example, sort by these yields, take a look at one of these molecules in here, and so on. So this is what the final app now looks like. Okay, before finishing off and having a final set of questions, I want to just quickly mention this. What was already mentioned, how do you then actually do this in an oasis and not just with this notebook kind of hacks. And the way you do it is that you write a NOMAD plugin. And what a NOMAD plugin is it's basically a Python package where you can define all of this stuff that we did before. You can define a parser, a schema, an app in there. So it's like a Python package that you install then on your NOMAD oasis. So pip install this thing, and then these things get registered in there and activated, and then that's it. But of course, there's now a lot of these details that I'm skipping here in terms of, if you don't know anything about writing Python packages, it might be like a rough start. You need to know certain basics of what a Python package looks like and things like that. We have prepared this particular example. We have a link here of this final plugin and what it looks like. So I encourage you to go here and explore this to understand more. We also have the documentation for plugins here. So I encourage you to also take a look at this. It goes through a lot of these things, what you should do to create these plugin packages, and how you define, particularly if you want to write a parser, for example, what you do. So essentially, these are the same things that we did here, with a few additional things on top. But the bulk of the work we actually just did already in the notebook, and it's just about getting the structure right and having the right things in the package setup. I think we need to wrap up now.